Greetings and welcome. We're talking today about writing equations of ellipses. We know how to write them in standard form. When they're given to us, we can find, the value of A, the length of the semi-major axis, B, the length of the semi-minor axis. You guys can find the foci, the center, all sorts of wonderful stuff. You could even look at the equation in standard form and determine immediately whether or not it is in, a horizontally or vertically oriented ellipse. Today we're going to talk about, first of all, general form of the equation of an ellipse. And then we'll also talk about writing equations of ellipses based on some facts or clues. And then we'll also talk about the concept of eccentricity, like an eccentric rich old person. Let's see, general form of the equation of an ellipse. And this is going to have some similarities to the equation of a circle that you've seen before. So this is the idea. It's going to have ax squared plus c, You might wonder where that capital B went, but it's intentionally not there for now. Plus cy squared plus dx plus ey plus f equals 0. And so this is the kind of general form of the equation of an ellipse. One of the things I want to point out is that little facts about A and C. A and C are, not equal to 0, and they in fact have the same sign. But they are not they're not equal to each other. If A and C were equal to each other and had the same sign, what conic section would this be then? It would be a circle when A and C are equal. And actually that brings up another point. This A and this C are not the A, little a, and B or C, little c, right? All of those things in the standard form. These are just like weird coefficients that do not necessarily relate through some math we'd be able to figure out like the length of some of those things, the semi-major axis and everything. But these are not the same as those, okay? So let's talk about an example. Here we go. Where we're going to translate from general form into standard form. So write in standard form. Standard form, bam, here we go. So let's say I've got the following, 4x squared plus 9y squared minus 40x plus 36y plus 100 equals 0. All right, so here's general form, and you'll see some similarities to our techniques when we were doing the same thing for circles. The first thing I'm going to do is group the x's and y's. So let's see, so I'll have 4x squared minus 40x plus 9y squared plus 36y, and I'll move that c term to the other side and make it negative. Now, I do have some blanks there. They're going to show up in a minute, but I actually can't do anything with those just yet. But my next move is I'm going to attempt to double complete the square. However, you may recall when completing the square that you weren't allowed to have a leading coefficient other than 1 for your quadratic term. All right. So what I actually have to do is, this isn't quite GCF. Actually, wow, I'm really disappointed that the book actually calls this the GCF. It's like a GCF. It's a common factor, it's just not the greatest. Man, that sounds like such a put down. It sounds like I'm breaking up with it. You're pretty awesome, you're just not the greatest. That's all. I'm sorry. Seriously, just move on, you'll find someone else. It'll be great. You're just not the greatest, that's all. So let's see. I'm actually going to factor a out here, all right? So even though I could factor an x out of both of these terms, I'm not going to. All right, so I'm going to factor a out. And over here, I'm going to factor c out. So here I'll factor 4. Over here I'll factor out a positive 9. So I'll get 4 times x squared minus 10x blank plus 9 times y squared plus 4y, I believe, blank equals negative 100. Man, it's hard to fit this all in one line. Yeah, there we go. And then double blank over there. So, all right. And you might remember some of this stuff from completing the square days as well. So I want to complete the square for the x's. So I'll have negative 10 over 2 all squared. Negative 5 squared equals 25. So add 25 in there. And now consider this. I'm adding 25 in the world of parentheses. But in the world of the problem, I technically added 4 times 25 on the left-hand side. Right? So I technically added 100. So to counterbalance that, I actually have to add 100 over here. All right, so that's a potential hang-up. I could have some really well-written multiple-choice questions just about that step and have a whole bunch of possible things like, what would you do on the right-hand side? Would you add 25? Would you add 4? Would you add 100? Would you subtract 100? Right? And there'd be all sorts of excellent, good multiple-choice questions I could have. So yeah, that's one of the things you have to realize is that in the world of parentheses, we added 25. In the world of the problem, we added 100. So that's why I had to balance that. So you could kind of think of this as it would just always be whatever your A was multiplied by your new C. But I think making a formula for that would just make things more confusing, if anything. So let's see. Let's complete the square for the y. So 4 over 2 all squared equals 2 squared, which equals 4. So I'm going to add 4 in the world of parentheses, which in the world of the problem was really adding 36. So to balance out the universe, I have to add 36 over there. All right, good stuff. And now, let's factor this. So I'll have 4 times, this is going to be x minus 5 all squared, right? That minus 5, can find it right there. Plus 9 times y plus 2 all squared, right? That 2 is right there, equals 36. Now, we're almost at the equation of an ellipse, but what is the equation of an ellipse always equal to when it's in standard form? 1. So what could I do to both sides to get this to equal 1? Yeah, let's divide everything by 36, right? I mean, I suppose I could also get that to equal 1 by subtracting 35, but that's just like, that also isn't bringing me closer to being the equation of ellipse. So I'm going to divide everybody by 36. And conveniently, because the book is super friendly and kind to us, this kind of conveniently cross-cancels a little bit. X minus 5, not cross-cancels, reduces. Really friendly for us. 4 goes into 4 once, into 36 9 times, plus y plus 2 all squared over 9 goes into 9 once and into 36 4 times, and equals 1. Voila. Voila. There we are. So yeah, so there you go. That's not too crazy. Not too crazy. And then you could figure out, oh, it's horizontally oriented. The value of A was 3. The value of B was 2. The center was 5, comma, negative 2. And you guys could run from there like champions. By the way, the more interesting cases kind of occur when this doesn't reduce perfectly, and then finding the value of A or B requires some interesting skills. But I don't think those problems actually show up all that often. Usually they end up being really friendly to us. But yeah, so but overall, I mean, this is not terribly different from the skills we already had. It just kind of adds like a degree of complexity with this here and stuff. So not that bad. Let's talk about eccentricity. All right. So not electricity, eccentricity, which is going to kind of describe the extremeness of our ellipse. Okay, so it's a ratio. It describes the shape of an ellipse, and we'll actually have the shape of an ellipse. And it's actually something that will show up in other conic sections as well, or at least hyperbolas. Yeah, I guess parabolas don't have an eccentricity. And E, the eccentricity, is defined as the ratio of C over A. And in an ellipse, it's also true. I just want to point out that 0 is less than C, which is less than A, right? These are both positive numbers. And in an ellipse, the distance from the center to the foci is shorter than the distance from the center to the point on the semi-major axis, right? That vertice there. So this is true. And notice, if I was to actually take this equation and divide everybody by A, what does this tell me about C over A? What's this equal?
0.
0, and this is 1. And since the eccentricity is equal to C over A, that tells me that eccentricity is a value between 0 and 1. So this is just kind of, it's not an equation, it's just kind of, it lets you know that the possible values of E, it's a number between 0 and 1. So I might actually steal this little snapshot right here. This is from our text. This is not my own work. This is whatever company this is. Page 638, blah, blah, blah. Copywritten, blah, 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 blah. Right? And so here's just kind of a nice little sketch. I'm not going to have you guys write this down. But for values of E that are close to 0, the foci are closer to the center. All right? And the graph, how would you describe that graph compared to this one? It's more circular, right? Where if the eccentricity is larger and closer to 1, right, the maximum threshold, which actually it can never equal 1, it just can get kind of close to 1, then the foci are far from the center. And how would you describe this ellipse? It's well, technically both of these are ellipses, but this is far from being circular. It's elongated, right? It's extreme. And so what I want to point out is that the mathematicians use the word to describe this as eccentric. All right? Which the only other time I hear the word eccentric used as kind of an adjective is describing a really rich old person that kind of has really interesting tastes. Like, I don't know, like, I like making horses drive cars and race them for my entertainment. Like, okay, I guess that's something you could do if you have a lot of money. You know, like they're eccentric. Like, I have an obscure collection of skulls of actors and actresses that played in Shakespeare's plays. Like, if you have enough money, maybe you could do that. That would be quite eccentric, right? It would be somewhat odd or eccentric. So this is an odd or extreme type of ellipse. It's like, okay, you can do your thing, ellipse. Your foci are really far from your center, right? You're a little bit far from normal for us, and that's fine. That is fine. So some of your problems might give you clues where they're like, the eccentricity is 0.7. And that might allow you to realize, oh, so the ratio of C to A is 0.7. So if I know E, the eccentricity, and I know A, I could solve for C. So it's just going to be an additional formula to help us solve for things is really all it is. All right. So let's actually do a clue problem, and then I think we might call it a video here. Write the equation of the ellipse in standard form. So let's find some nice clue problem for us. Let's say, that one's a little bit too on the nose. Ooh, this one's a devious one. I'm tempted to do it though. Now let's do this one. Let's say that the center is at the point 3, 1. And let's see, the vertical semi-major axis is 6 units long, and the eccentricity is 1/3. So eccentricity of 1/3 is telling me that it's closer to 0 than it is to 1, so it's a little bit more circular in shape than super elongated, right? So let's, based on these facts, let's write down what we know. So I know that H is equal to 3. I know that K is equal to 1. That's good stuff. The vertical semi-major axis. So if the semi-major axis is vertical, what is the orientation of the ellipse? Semi-major axis, that's the longer one. So the ellipse is also vertically oriented, right? If this said semi-minor, don't just assume because you saw the word vertical that it means the ellipse is vertically oriented. So I know that this is vertically oriented. And let's see, if the length of the semi-major axis is 6 units long, what does that tell me? What does that represent in terms of my variables? So A is yeah, for the if I was actually finding the locations of the vertices, I would add and subtract 6 from K. But the value of A is 6 units long. All right, so and if they just told me, actually, I just realized I missed the I in semi. I just wrote sem major. Anyways, but if they just told me it was the major axis, then A would have been half of that number, right? So I just want to point out, like, the clues can be given to us in many different forms, and we'd have to find them. So let's see, what else do I need to know? I need to figure out what is B equal to and what is C equal to. And that would be enough information for me to work with. And I think I've got a couple of things that might help me out. I know that A squared minus B squared is equal to C squared. So that's one relationship. So I'm looking for 2 variables. But I fortunately also have 2 equations. And I also know that the eccentricity is equal to C over A. Right? So I'll have 2 equations and 2 unknowns. I'll be able to solve a system using Cramer's rule, matrices, substitution, elimination. I just called it elimination as if there was no E in front of it. If I just got, man, I think that would be eccentric of me if I just pronounced all of my E words without the E. I just made them all silent. That would be intriguing. So let's plug in what we know and solve for what we don't eventually. So, so this one is A squared is 6, so 6 squared minus B squared equals C squared. Let's plug in what we know here. This is 1/3 is equal to C, I still don't know, over A, I do know. So between these 2 equations, what could I do to solve for B and C? Where do you want to start? I kind of like the right-hand side myself because this one's got all like squares in it. That would also reciprocate this, and then I'd be solving for 6 over c. Well, how could I get c by itself over here? Yeah, multiply by 6 on both sides. And I get c equals 2, or 2 equals c. Right? And now I could then just be like, aha, substitute. Right, like so. So I'll have 36 minus b squared equals 2 squared, which is 4. So negative b squared is equal to negative 32. B squared is equal to positive 32. And then root both sides. And I will get b equals square root of 32. Is there a perfect square that goes into that?
16.
Oh, wow. That's even better. I was going to say 4, but better yet, if we can find the largest perfect square, it'll reduce all in one fell swoop instead of multiple reductions being required. Square root of 16 is 4. Square root of 2. So there's the value of b. Yay, we found c, we found b, we got everybody. And we also know that it's vertically oriented. So my equation that I'm plugging this into is x minus h squared. I'm just going to rewrite it for the sake of our notes. You don't have to write this down if you already have this stuff mastered. Y minus k all squared over a squared equals 1. So let's plug in what we know. So let's see, the center was 3, 1. So x minus 3 squared. Y minus 1. Wait, positive 3, right? And positive 1. It was positive for both of them, I think. So these would be minus signs, yeah. Equals 1. Let's see these denominators. A was equal to 6. So 6 squared is 36. And B is equal to 4 roots of 2, or the square root of 32. And if I square that, I get 32 over here. So kind of some interesting ways you can get problems like this, where you have all sorts of stuff that you can do. Not too shabby. So thanks for watching, internet friends. Have a great day. Bye-bye.